All right, so today we're diving into something pretty big. We're talking about Einstein's genius,
Hmm.
Einstein's theory of relativity. But, and this is the really interesting part, we're going to be looking at where it sort of falls apart,
Yeah.
where the edges are. And we're doing a deep dive on this, so it's
Yeah.
going to be interesting to unpack.
Yeah. Einstein's theories, especially his theory of special relativity, really revolutionized how we understand um, space and time.
Hmm.
But the great thing about science is that
Yeah.
it always wants more, right? It's always pushing the boundaries, looking for what's beyond what we currently understand.
It's like climbing to the top of one mountain and then you get to the top and you're like, oh, there's a whole other mountain range over there. So I gotta ask, I mean, just to set the stage, when we talk about relativity, I think a lot of people, myself included, we hear that word and it's a little intimidating, right? It feels very complex.
Yeah.
What are the really like ground floor basic things that people should have in mind as we kind of go on this journey?
Yeah, so when we talk about Einstein's theory of special relativity, he really based it on two main postulates. The first one is relatively straightforward, no pun intended,
Hmm.
but it basically states that the laws of physics are the same everywhere in the universe,
Okay,
as long as you're not accelerating.
gotcha.
So it doesn't matter if you're here on Earth or if you're, floating out in space. The laws of physics, gravity, how things move, it all behaves the same.
Universe has to have some rules, right?
Specifically.
Some
Right.
consistency. Okay, so that's one. What's the second one?
So the second one is where things get a little bit more juicy. This is where he introduces the speed of light.
Okay.
And this idea that the speed of light in a vacuum is constant for all observers,
Yeah.
regardless of how fast they're moving relative to that light source.
Okay, so break that down for me.
Okay, so imagine you have like a flashlight, right? And you shine that flashlight.
Hmm.
We know light travels incredibly fast, about 300,000 kilometers per second. Now imagine you're in a spaceship
Okay.
and you're traveling at, say, half the speed of light,
Okay, so we're moving really, really fast.
really fast.
Yeah.
And you shine that same flashlight. Now, you would think, right, that the light coming out of that flashlight is traveling at the speed of light plus the speed that you're already going, so it would be even
Yeah.
faster.
Right, right. It would add on, yeah.
But it doesn't. That speed of light,
Yeah.
it's constant.
It doesn't matter how fast you're already moving.
It's
Like a universal speed limit.
You got it.
Okay.
You got it. And this is really where things get kind of crazy.
Yeah.
Because what it means is that time and space themselves are not absolute, but they're relative. And this is where we get into things like time dilation
I
and
know.
length contraction.
Okay, now those sound like we're getting into like science fiction territory now. We're
Yeah.
talking time travel.
Not quite time travel,
Okay.
but close. Right.
Okay.
But let's talk about time dilation.
Okay.
So imagine you have a clock that is, a perfectly accurate clock. And this clock is moving past you at an incredibly high speed, close to the speed of light. Now, relativity tells us that that clock, the one that's moving super fast,
Yeah.
will actually appear to pass slower relative to a clock that's stationary relative to you.
So you're saying time itself is different
Yeah.
depending on how fast you're moving?
Yes.
That's wild. How do we even know that that's like a real thing?
Yeah, so there's actually quite a bit of experimental evidence that confirms that this is happening.
Wow.
One of the most, I think, interesting examples of this is with these particles called muons.
Muons.
Muons. So muons are these subatomic particles. They have a very, very short lifespan,
Okay.
meaning they decay very quickly.
Okay.
And muons are created high up in the Earth's atmosphere by these things called cosmic rays.
Okay, so they're like these little speedsters that are just like constantly popping into existence.
Exactly.
Obviously.
They're zipping around at close to the speed of light. And because they're traveling so fast, we actually observe way more muons reaching the Earth's surface than we should if time was constant for everyone.
Okay.
So their high speed actually stretches out their lifespan from our perspective.
So time slows down for them essentially,
I see.
allowing them to travel further before they decay.
Exactly.
Wow. That's mind-blowing. So this isn't just like a physics problem on a chalkboard.
Right.
This is actually impacting like stuff that's happening above our heads all the time.
All the time. And it actually has real-world implications, too. Our source material mentioned GPS satellites. They actually have to account for this time dilation.
Wait, are you serious? Relativity is messing with our navigation.
It is.
How does that even work?
So these GPS satellites, they're constantly moving around the Earth, right? And because they're moving, their clocks are actually running slightly slower compared to clocks here on the ground.
So if we didn't account for relativity, like our phones and stuff, we'd
Huh?
be getting lost all the time.
You would have some very inaccurate GPS coordinates.
Oh, that's wild. Okay, so we're seeing that, even in very practical ways, this theory is kind of playing out.
Absolutely.
But I feel like we've kind of just scratched the surface a little bit here because our source material was mentioning that as amazing as this theory is, as much as it seems to explain, it's not perfect. There are places where relativity sort of breaks down. So what's the deal with that?
Yeah. So no scientific theory is sort of the be all end all.
Right.
Right. We're always refining and trying to find, better explanations, more accurate explanations.
Sure.
And one of the biggest challenges for Einstein's relativity is actually trying to make it jive with another cornerstone of modern physics, and that's quantum mechanics.
Ah, yes, quantum
Yeah.
mechanics, the weird, wacky world of the very, very small.
Exactly.
I
Right.
always
Yeah.
imagine like subatomic particles and they're just like zipping around and doing all this crazy stuff that we can barely even wrap our heads around.
It's a very counterintuitive world.
It really is. Where's the conflict? Where do these two kind of giants of physics bump up against each other?
Yeah, so I think it's helpful to think about this in terms of like the scales that we're talking about. So relativity loves a smooth, continuous universe, right?
Okay.
Space-time,
Yeah.
you can kind of picture it almost like a sheet, that could be bent and warped by massive objects
Okay.
like stars and planets.
I've heard that analogy before.
Right, right. But then quantum mechanics comes along and it says, well, not so fast. Um, at the subatomic level, things get a little bit more chunky,
Right.
more uncertain, almost like pixelated,
Yeah.
It's like trying to draw a perfectly smooth curve on your computer screen. You can get close,
Right.
but you're ultimately limited by the pixels that make up that screen, right?
Yeah, you get kind of a jaggedy version of it, not the real deal.
Exactly, exactly. And so quantum mechanics says that things like energy, momentum,
Yeah.
and even space and time itself, they come in these discrete chunks,
Oh,
these
yeah.
little packets of energy called quanta. And so that's really where the heart of the conflict lies, right? You
Mhm.
have this smooth, continuous picture from relativity,
Yeah.
and then this kind of chunky, pixelated reality from quantum mechanics.
Right. So it's almost like these two theories are speaking different languages.
Yeah.
They're describing different aspects of the universe, but they can't quite talk to each other.
Yeah, and that's a huge, uh, it's a huge problem for physicists, right? Because
Yeah.
the holy grail is to find a way to unify these two theories, right?
Yeah.
To come up with what we would call a theory of everything or a theory of quantum gravity.
Right.
Um, and
A theory of everything. No, there's a deep dive. I'd sign up for that one.
right, exactly,
Yeah.
exactly. But it's a puzzle
Yeah.
that we're still trying to figure out.
Well, speaking of puzzles and speaking of things that are hard to wrap our heads around, our source material also mention black holes.
Yeah,
And black holes, I mean, those just seem like the ultimate nightmare scenario for relativity.
they really do. Black holes are where things get really, really strange.
Yeah.
Even for a theory as bizarre as relativity, right?
Right.
So essentially you have these regions of space-time where gravity is so unbelievably strong
Yeah.
that nothing, not even light,
Right.
can
No.
escape.
Okay.
And it's at the very heart of a black hole, this point that we call the singularity is this point of infinite density
Oh,
where our current understanding of physics it breaks down.
Wait, so you're saying that relativity is supposed to be explaining gravity, but it gets to the singularity of black hole and it's just like, I don't know.
Essentially, yeah. The equations that we use to describe gravity, the ones that Einstein gave us, they start to give us nonsensical answers.
Okay, so it's not even that we just don't have the tools to observe what's happening.
Right.
Our theories themselves are just like, nope, not going to do it.
Yeah, they stop working.
Oh, well, that's both terrifying and exhilarating at the same time.
It is. It's really quite remarkable.
Yeah. Yeah, okay, wow. So even with this theory, right, that we're talking about that has done so much to advance our understanding, there's still
Yeah.
so much that we don't know, which is kind of what makes it all so fascinating. So we're seeing that even with a theory as groundbreaking, as revolutionary as Einstein's relativity, there are still these huge mysteries, these places where it just doesn't quite work. Which I guess, I don't know, that's kind of what makes it exciting.
Absolutely.
It means there's still more to discover. There was one more thing in our source that really kind of caught my eye, and it was this idea of observer dependence, which almost sounds like, I don't know, it sounds like we're getting into like philosophy almost
Yeah.
instead of physics. What is that all about?
Yeah, it is a concept that definitely has some philosophical implications because you see, when Einstein came up with the theory of relativity, it really shifted our perspective
Yeah.
away from this idea that there's some absolute frame of reference, right? Like
Yeah.
there's some universal clock out there that dictates time for everyone and everything in the universe.
Yeah.
And what he showed is that what we observe, how we perceive time and space,
Yeah.
actually depends on our motion relative to whatever it is that we're observing.
So you're saying, like, my experience of time might not be the same as someone else's, that there's not just like one clock for the entire universe.
Exactly.
Yeah.
Yeah. There's no universal clock, and that's kind of a mind-blowing thing to think about, but it's true.
That is really strange. Like, how do we even begin to, I don't know, wrap our heads around that? Are there examples of that, like in the real world, or is that more of a like a thought experiment kind of thing?
So so think about it this way.
Huh.
Imagine you have two events that are happening really, really far apart, like on opposite sides of the galaxy. Okay. Now, relativity actually allows for the possibility that one observer might see those two events happening at the same time, simultaneously,
Okay.
while another observer who's moving differently relative to those events might see them happening in a different order.
Wait, hold on. So you're telling me that even the order of events can be relative. So like what does that even do to like cause and effect? Does the universe just become like totally chaotic?
It's a good question, and these are definitely things that physicists are still,
Yeah.
trying to grapple with and understand. Relativity still very much holds on to the fact that causes happen before effects.
Okay.
That hasn't been completely thrown out the window.
Right.
But how we understand that, how we understand things like simultaneity being relative,
Right.
those are still open questions.
Wow, okay. I'm starting to see why they call it relativity. It's all relative. This is definitely making my head spin a little bit. I mean, we started out talking about the speed of light being constant, and now we're in a world where time is like fluid and black holes break our physics and like, the order of events might be subjective. It's a lot. So if there was like one big thing that you would want someone like me or any of our listeners who are kind of dipping their toes into this for the first time, what would you want them to kind of walk away with from all of this?
I think the biggest thing is just to remember that, Einstein's theory of relativity, as strange as it might seem,
Yeah.
it's really a testament to human ingenuity, right?
Yeah.
It's our attempt to understand this incredibly vast and complex universe.
Yeah.
And even though we don't have all the answers,
Right.
and even though there are these areas where the theory breaks down or we run into things you don't fully understand, that's okay. That's part of the beauty of science.
Yeah, I love that. It's about the journey.
It
It's
is
not about having all the answers.
exactly. It's about the journey, and it's
Yeah.
about being open to the possibility that, this universe that we live in is far more amazing and strange than we could possibly have imagined.
I love that. And who knows what incredible discoveries are still waiting out there for us, right? I mean, we didn't even get a chance to talk about the twin paradox.
Right, exactly.
But, all the more reason to keep exploring. Well, for the deep dive, this has been your host, signing off. Keep asking those big questions out there, folks, and we'll see you next time for another deep dive.